Hi, welcome to Unit 6, Day 8, Intro to Empirical Formulas. So in this part of the lesson, we are going to do the following. We're going to understand the information provided by chemical formulas. We're going to talk about and recognize the difference between empirical and molecular formulas. And we're going to be able to determine an empirical formula from a molecular formula. So let's start by reviewing what we know about chemical formulas. Chemical formulas provide a wealth of information about a molecule. For example, they tell us the types of atoms in a molecule. They can give us the actual or relative number of atoms in a molecule and the ratio of atoms either to each other or to the molecule that they are in. So let's take a look at that for these three structures here. The first structure has a chemical formula of H2O, it's water. The second structure has a chemical formula of CH3COOH, or you can sort of condense this into C2H4O2. And the final one, sodium chloride, has a chemical formula of NaCl. Now we can tell from all three types of chemical formula, first off, the types of atoms that are in them. For example, starting with water, water is made up of hydrogen and oxygen atoms. We can see that vinegar is made up of carbon, hydrogen, and oxygen atoms, and sodium chloride is made up of sodium and chlorine atoms. We can also determine the actual relative number of each atom in the molecule. So if you look at the chemical formula of water, you can see that it has 2 hydrogens and 1 oxygen atom. And so that will be the actual number of each atom. For vinegar, we can look at the chemical formula and see it has 2 carbons, 4 hydrogens, and 2 oxygen atoms. So again, we know the actual number of atoms in that molecule. For something like sodium chloride, which is an ionic compound, and remember for ionic compounds, the bonds are not discrete, they're in a network or a lattice. The information that we can get from this is the relative number of sodium and chlorine atoms. And the reason why I say relative is because if you had a chunk of sodium chloride, you're going to have a ton of sodium and chlorine atoms. However, if you focus on just one unit, you know that you have 1 sodium for 1 chlorine atom. Now let's go into the ratios. We also can get information about ratios of atoms, and this information actually is going to be useful for the next unit on stoichiometry. So if you look at a water molecule, for example, if you look at the chemical formula H2O, you can see that there are 2 hydrogen atoms for each water molecule. So that would suggest a 2-to-1 ratio, 2 hydrogens for 1 water molecule. So in this case, for this ratio, we're comparing the number of atoms to the entire molecule. We can also compare determine the ratio of atoms within the molecule. So for example, for vinegar, it has 2 carbons and 4 hydrogens. So in vinegar, we can say there's a 2-to-4 or 1-to-2 ratio of carbon to hydrogen. And likewise, for sodium chloride, we can say there's a 1-to-1 ratio of sodium to chlorine atoms. Okay, so this is quite a bit of information that we can get from the chemical formula. But did you know there are actually 2 types of chemical formulas? The first type is the molecular formula, and that's the one we're probably most used to. It's the chemical formula for the actual molecule. So for example, if you look at benzene, benzene is made up of 6 carbons and 6 hydrogens, so its molecular formula would be C6H6. But there's also the empirical formula, which is more like a simplified version of the molecular formula. And the empirical formula is a chemical formula with the smallest whole number ratio of atoms in a molecule. So for benzene, the empirical formula is CH. Now you may be asking, how do you get that formula? Well, what we do to get the empirical formula is we simplify the subscripts in the molecular formula. And the way that we do that is we look for a least common factor, a number we can divide out of all of the subscripts. In the case of benzene, C6H6, the least common factor is 6. So if we divide out a 6 from all of the subscripts, we get the empirical formula CH. Now, just a quick note, ionic compounds use empirical formulas only. So remember, for ionic compounds, since they're not discrete, they're in a lattice or a network, their empirical formula and molecular formulas are going to be the same. Here's some more information about empirical formulas. So one thing that's important to know about empirical formulas is that some molecules will have the same molecular formula and empirical formula. So examples of that would be something like formaldehyde. Its molecular formula is CH2O. Now, if you look at the subscripts 1, 2, and 1, you can't simplify that any further. So the empirical formula will be the same as the molecular formula. Similarly, for something like dinitrogen pentoxide, if you look at the molecular formulas N2O5, the subscripts 2 and 5, you can't simplify that any further. They don't have a least common factor other than 1, so the empirical formula will be the same. And then finally, something like table sugar. Its molecular formula and empirical formula are the same as well because you can't simplify the molecular formula any further. And also, of course, remember for ionic compounds, that is always the case since the chemical formula of ionic compounds will always be the empirical formula. Now, it's also important to note that different molecules can have the same empirical formula. So if you look at these molecules below, the molecular formulas are shown in blue, and the empirical formulas are shown in that sort of pinkish color. And all of these molecules have the same empirical formula, CH2O, but they have different molecular formulas because you can simplify them. You can simplify the molecular formulas all into CH2O by using whatever the least common factor is for that molecule. All right, now let's go ahead and try our first CFU. Acetylene, C2H2, has the same empirical formula as benzene, C6H6. True or false? All right, so go ahead and pause the video now, and when you press play again, if you need to, there will be a hint provided, followed by the answer. So if you need a hint, what you want to do to answer this question is determine the empirical formulas for acetylene, C2H2, and benzene, C6H6. Now, we've already determined the empirical formula for benzene in the previous slides. And remember, the way that you do that is you find the least common factor that you can use to basically simplify the subscripts. Can you simplify these numbers like you would do in algebra? Right? So if they have a least common factor, you would divide all the subscripts by that least common factor, and then that will give you the empirical formula. Then you're just going to compare the two to see if they're the same. So if you need to, you can pause the video and try and solve this. If not, the answer will be revealed in about 3 seconds. All right, the answer is true. So the empirical formula for benzene is CH, and the empirical formula for acetylene is CH. And you can see that work shown here. So in benzene, the least common factor, to simplify it out, is 6, and then for acetylene, it is 2. All right. Final thing we're going to talk about is why is all of this important? Why is it important to know empirical formula? Well, when a chemist performs a reaction, they need to confirm that they've actually made their product by identifying what it is that they made. Sometimes you can tell just by looking at it, but a lot of times, especially for more complicated reactions, you can't. And so one technique that chemists use to identify their compound is elemental analysis. So the data that you get from an elemental analysis experiment can be used to determine the empirical formula, which then can be used as evidence for the identity of the product. So if you get an empirical formula that matches your product, you can say that this suggests that I do have my product. So what's elemental analysis? What's that experiment look like? So typically what happens in elemental analysis is that you take a sample of your product, what you hope is your product, and run it through a machine that looks something like this. And then that machine will produce a plot of some data. And the main part of that data, if you look here, is the mass percent of all of the elements in that sample. Remember now, the mass percent is the mass of each element in a molecule divided by the total mass times 100. And we did that sort of earlier in the unit. So essentially, you're going to get the mass percent of each element. Then from there, you will take the mass percent and use it to get the empirical formula. Now, if you're in honors chemistry, that's going to be the next part of this lesson that's required for you. For fundamentals of chemistry, that process of going from mass percent and empirical formula is optional if you choose to do it. All right, but let's take that knowledge that we sort of talked about in the previous few slides about using empirical formula to help you identify a unknown. So in this CFU, it says an unknown substance has an empirical formula of C3H6O. Based on this information, which of the following molecules could be the unknown substance? Select all that apply. Pause the video now, and when you press play again, the answer will be revealed. Great, so here are the answers B and E. So in B, the least common factor is 2. That means you can simplify the subscripts 6, 12, and 2 by dividing them all by 2, right? And then when you do that, you're going to get C3H6O. The last choice, E, is also correct because the molecular formula, which is C3H5OH, is also equal to C3H6O, right? Remember, you can just basically move that hydrogen, put the hydrogens all together. And so instead of splitting them out, it'll become C3H6O. And this molecular formula matches the empirical formula. Now remember, a molecule can have the same molecular and empirical formula. All right, so that is it for this video. For fundamentals of chemistry, you can go straight into the exit ticket from what you covered today. For honors chemistry, after doing the exit ticket, then you have to do this part too. All right, folks, have a quality day.